Sorry, what were you saying?
Oh, I'm chairing the session, so.
Oh, you're chairing. Okay, okay. I see. I see.
Yeah, because we're all set to go. We're all started.
Yeah, once you know this.
Yeah, but.
So are you live streaming it or you're recording it? I see. Is this on? Oh, yeah, it's on. Oh yeah, I'll finish 10:05. Yeah.
All right, good morning, everybody. Glad to see you here. Grateful for a second day of the conference. Our first talk today is by Timo Seppäläinen, talking about Busemann processes, and very excited.
Thanks, Evan, and thanks very much to the organizers. It's great to be here. So Jeremy and I both graduated around 1990. Jeremy a few years before me, and we thought it would be sort of amusing if I tried to convey a little bit to you how different those times were and how difficult our formative years were. So many things sort of collided at the time. Geopolitical events conspired to completely kill the job market. So many of the people we went to grad school with, they just kind of vanished off the face of the earth. And some of us survived just by luck, I guess. The tenor of the field was also very different. An event like this, in probability, with so many young people, would have been inconceivable. It would not have happened. And this idea of mentoring that's so ubiquitous today and pushed by all the people who fund us, this was almost a dirty word at the time. The idea was that you find your own way and you fight your own way into the community in competition with the seasoned guy. And it wasn't that people were cruel, but the thinking behind this was that math can be a harsh career. So rather than draw people in, like the prominent philosophies today, the idea was to keep the threshold high, so that only those who refuse to do anything other in their life end up in these careers and into those few academic jobs that are out there. So it's just so different today. And we can see it in our field, this huge explosive development. It's partly because nowadays we make young people into partners early on. Back then, there were no joint papers between advisors and students. You were sort of pointed into a direction, go find something there. And that's how some of us then survived. All right, so on that, on that happy note, so let me tell you something about Busemann functions. the term already was mentioned a few times yesterday, and of course many of us know what they are, and maybe some of us don't. So I'll try to give a quick introduction to how this thing came into random growth models. So here's a plan for the talk. For sure, way too ambitious. So I'll probably get through the second bullet. So I'll start with a quick introduction, and the main point of my talk is that I want to show you how something called the geometric Robinson-Shenstedt-Knuth correspondence helps us to identify or describe the distribution of the Busemann process in these models. And I'll concentrate in particular on one example, and that's the solvable lattice polymer model, the inverse gamma model. In the third bullet, I want to illustrate how the Busemann process can also be used as a tool. I'll try to talk to the microphone to get the results about these models, and I'll probably have to end up there. But if there's time left, I'll try to say something about the continuum models also, in particular the KPZ equation. So there's Herbert Busemann. He had an interesting life. He came from a rich business family. His father wanted him to go into business. He tried that, but didn't like it. Went to do a PhD in mathematics. He got it in 1931 with Richard Courant in Göttingen, about whom he didn't have anything positive to say. He had partial Jewish background in his ancestry, so he figured it's best to clear away from Germany. So in 1933, he went to Copenhagen, and in 1936, he ended up in the US, and here he stayed. He kicked around in various jobs, and in 1947, he landed at University of Southern California, where he then stayed for the rest of his career, retiring in 1970. He wrote several influential books. He had quite a few PhD students, so all in all, a very prominent career. All right, so that's how the geometers define the Busemann function these days. You have a metric space, you have an infinite geodesic there that's parameterized by arc length. So then they prove that this limit here exists, and I have a red point there. So that limit there is the Busemann function, and in particular, it was first presented in Herbert Busemann's 1955 award-winning monograph on the geometry of geodesics. So a few decades later, it then made its way into probability. So I think the first time when someone actually explicitly defined something called the Busemann function was Chris Hoffman in 2005 in first passage percolation. So you see, it differs a little bit from that geometer's definition. We have to normalize it a little bit differently. So the tau there is the passage time in last passage percolation. So this definition assumes that you have an infinite geodetic to begin with, but we actually want to often do something a little different with this notion in stochastic growth models. We want to not start by assuming a geodesic, but we want to use this notion to study the existence and uniqueness and properties of geodesics. So then let's back up a decade, and there's Chuck Newman's definition from 1995, again in the context of first passage percolation. So a geodesic is now not assumed, but instead you take a direction vector xi, and you try to prove this limit here. So it's a difference of passage times from x and y to that point Bn, which is receding to infinity in some particular direction. So it's a different definition. Hoffman's limit exists pretty easily in first passage percolation, but this limit is tricky. That's highly non-trivial, and you need something in order to be able to prove it. You can't just prove it without nothing to go with. So what Chuck and his collaborators proved back in the 90s was that in planar first passage percolation, if you make curvature assumptions on the limit shape, then you can prove that this limit holds for a given direction. So this definition has proved incredibly valuable for the field because there are many models where you can verify this curvature hypothesis. In particular in the exactly solvable cases, but also in others where you have, say, some kind of a quadratic Hamiltonian, you can often, or some, say, spatial homogeneity, you can often then verify that hypothesis and build this Busemann function, and from there geodesics, etc. So people have used this to great benefit ever since it came on the field. But at times we would actually like to start with even less, maybe start with nothing, even no hypothesis on the limit shape. Jack Hansen and Michael Damron came up with a weak convergence approach to that limit up there. What they basically did was they took advantage of the old Markov chain idea that if I want to prove something, if I want to prove the existence of an invariant stationary distribution for a Markov chain, what I do is I run the chain and I Cesaro average the distributions along the way, and with some compactness, I get a distribution. So Damron and Hansen did that to the Busemann process. They proved the existence of sort of a proto-Busemann thing with a weak limit. And then around the same time, Nikos Georgiou, my former student, and Firas, my longtime collaborator, we built this general Busemann process thing for nearest neighbor last passage percolation, and then Christian Gigen and Firas a little later for the directed polymer. So let me actually go through quickly this last definition here as a starting point. So we're doing directed paths on the planar lattice with some positive IID weights. And we can either play last passage percolation, which means that we maximize the weight of the path, or then we do a directed polymer, which means that we take the logarithm of the partition function. In other words, we sum over the paths between 2 points, multiply weights, take logs. And then we can build this so-called Busemann process in 2 steps. First, you do these limits that depend on a direction for a countable dense set of directions. So how do you do those limits? Where it depends now on what you start with. If you're in an exactly solvable model, or if you have the Chuck-Newman hypothesis on the limit shape, you can do almost sure limits. If not, you can follow the Damron-Hansen weak convergence approach. But by some hook or by some crook, you get this initial thing, and then you use planarity to your advantage, and you take left and right limits in this direction parameter. This works only on the plane because of certain monotonicity properties. But then in the end, you have this object here at the bottom, which is which is what we call the Busemann process. So it's a random process, and it has 4 parameters. There's 2 lattice arguments, x and y. There's the direction vector zeta, which I'm now taking in this line segment here between the two unit basis vectors. And then there's a sign, plus or minus. The plus sign gives a right continuous version. The minus sign gives a left continuous version. But it's convenient to keep them both for the geometric consequences that one wants to derive out of this thing. And it turns out that the jumps themselves are really useful and valuable. They're really an inherent feature of this thing. So you don't want to try to sort of hide them away. All right. Now, the goal is to make this object into a tool to study properties of either the growth model or the polymer model. So for that reason, you'd like to understand something about this distribution. So I'm going to sketch here an approach for describing that distribution that's dynamical. So we're going to take advantage of the fact that we can think of the Busemann process as evolving on the lattice. So actually, let me back up one slide here. So I wrote here southwest paths. So I'm changing the usual convention a little bit. So my geodesics go southwest, downward. And I'm doing it this way so that then when I take the time direction on the lattice to be the vertical upward direction, then the Busemann functions evolve and always see fresh, new, independent weights, if you can sort of picture this in your mind. So here in this slide, I'll try to explain this. So fix n direction vectors, and now I'm looking for the joint distribution of these n Busemann functions. So vertical direction represents time on the lattice. And now if you can picture this in your mind, so the Busemann function on a level on the lattice depends only on the weights below that level. So the weights above are fresh and independent. And if I imagine going from level t to level t plus 1, then there's a deterministic mapping that takes as input the level t Busemann function and the weights on the next level and outputs the next Busemann function. So in other words, I have a Markov chain. The state of the Markov chain is now an n-tuple of bi-infinite real-valued sequences. And the first theorem is that the distribution of these Busemann functions on level t is the unique translation ergodic stationary distribution of this Markov chain. It's unique once you specify the means, like these things often work out in interacting particle systems. So notice that. So now I'm restricting attention to these nearest neighbor Busemann functions here, and and it's out of those that I put together this this BT thing here. Yeah.
If you look on a general downright path, kind of define Busemann process on that, does I assume the same theorem?
Yeah, the same thing would be true. Yeah. That's true. So Ivan's point is that the horizontal line would be replaced by various other downright going paths. Yeah. So the question is really, in what situation can you extract some useful information? Yeah. So that's a definition of that distribution, but for some reason this definition hasn't really opened up in a useful way, neither in positive or in zero temperature. So the name of the game is to look for an alternative description that would enable us to get something explicit out of this. So the strategy will be the following. I'll look for an auxiliary process that's also driven by these same weights, hopefully in a natural way related with the thing that I want, and hopefully this auxiliary process will be more tractable, have more accessible properties than the Busemann process itself. So here's the picture. So on the one hand, I have the Busemann process evolving in time. So there's a mapping that takes me from level t to t+1, and it has the weights as a parameter. And then at the same time, I'm going to run this other process, also driven by the same weights, but with a different mapping. And I'm hoping to intertwine them. So I'm hoping that this picture here is a commutative diagram with an explicit mapping D. And the benefit I get out of this is that if I can identify a stationary distribution on the left, the mapping D pushes it into a stationary distribution on the right. And then the uniqueness theorem tells me that that's the thing I want. Okay. So now I want to go a little bit into details about how to construct that process I. And to do so, I have to choose now between doing last passage percolation or doing the polymer. So let me do the polymer, since last passage percolation is more often discussed. And this is where the geometric RSK features come in constructing this process I. So the next 3 slides will be a somewhat technical presentation of some of these GRSK details. So if this is new to you, just lean back and take in the general spirit of the things. Those who know GRSK will probably see some familiar things. So a basic building block of geometric RSK is a mapping called geometric row insertion. And those are the basic references up there: Kirillov 2001, Nomi and Yamada 2004. So this is a mapping that takes in two vectors of numbers, C and B. And it outputs 2 new vectors, C prime and B prime. And there's this is the conventional notation for it, this kind of a cross thing. And these are the formulas. And if you want to see something here that is maybe familiar, if you look at the middle equation there, you can perhaps see the spirit of a directed polymer evolving there. And the jargon that's used in this situation is people say that this word B is row inserted into the word C. And if I want to highlight one feature here for you, notice that in this mapping, when B, my point here, oops, when B becomes B prime, it's shortened by 1 position. So see, it started with indices L to N, and you end up with indices from L plus 1 to N. So this shortening is connected with the following situation, that the standard earlier application of this mapping is to a matrix of numbers, and the output is a triangular array. And it sort of proceeds like this, that you have an array of numbers that you're dynamically updating. So you're feeding in this new input B, and you're hitting this first diagonal C here, and then the next B prime hits the next diagonal. And in a triangular array, the diagonals always keep shortening. So shortening the B is consistent with this output. Now, in the Busemann picture, we want a stationary thing. So we actually want a rectangular output. So that's why I'm going to change this description suitably to fit my needs in just a moment here. So here's sort of the high-level outline of how I'm going to construct the process I. It's going to come from a collection of polymer partition functions indexed by the upper half plane. So the KT index there comes from the upper half plane, K horizontal, T vertical, time, and there's capital N of these collections of partition functions, and the process, and their ratios then will define the process I that I want. And there will be two inputs, boundary conditions which sit on the x-axis, and then above that bulk weights, those omegas. And then the process will go like this. It sort of starts at k equals -infinity, and then you do the geometric row insertion from 1k to the next, going off to +infinity. And at each time you update, you create a new vector of partition functions. This dot here represents the index t, the vertical index, and the k. And at each step of geometric row insertion, the k index is updated by 1. And each time you insert boundary conditions and you insert new weights, and this is how you calculate new partition functions. And here it is in a diagrammatic way. So imagine that the k index started way out there in the left at -infinity. And now I'm telling you how to update from k + 1 to k. So there I have a vector of partition functions, and I'm feeding in a boundary condition and some bulk weights, doing an instance of geometric row insertion. So out comes a vector of partition functions indexed by k, and new weights with a superscript 2. And now I have to counter the fact that the row insertion step shortened the input by one step, by one unit, by one coordinate. So I'm going to augment the output omega here by adding another boundary condition. And now I do another row insertion step, and so on until I've constructed the partition functions on the right up to capital N. And then I go from k to k + 1 all the way to the right. So this way it progresses. It can be formulated so that it started at -infinity. I can take the capital T to +infinity. And now I have an entire upper half plane indexed collection of polymer partition functions. And then I define my process I by taking these nearest neighbor horizontal ratios of partition functions. Okay, so let's go back to the beginning. What was the whole purpose of this exercise? It was to create this process here on the left that is intertwined with the Busemann process, and this construction. The point of the construction is that it works. There is an explicit mapping D. The D mapping also involves geometric row insertions, and the two are now intertwined. So up to now, everything has been general in the sense that the weights are just real numbers. They're not completely arbitrary. They have to satisfy some asymptotic conditions because I'm looking at infinite sequences of things. But nevertheless, there hasn't been any probability distribution yet. And now I'm going to specialize to the inverse gamma distribution so that I can get something explicit out of this. Yeah.
How should we think, I guess the D hasn't been given yet. The D depends on the distribution of the W's, or the D is...
No, this is all purely algebra. Yeah, so that's right. There's no probability here yet. It's just algebraic manipulations and assumptions on the asymptotic assumptions on the weights, so that their empirical limiting empirical means are in the right order, so that these mappings are well defined. But that's all.
Is there an interpretation of what the I's mean?
Beyond the fact that they are ratios of polymer partition functions, not really. If you're in positive temperature, this whole picture has a natural queuing interpretation. So this is in a sense detropicalizing the queuing situation. That would be another way of putting it. Okay. Yes.
So if I think of the Busemann function as a solution to the Stochastic equation, then okay, I guess it's related to the question I might ask. I'm curious whether this I solve the 13 equation.
I'm not sure about that, but certainly this picture repeats in the continuum situation. And in that case, what you will have on the left-hand side of the picture is certain things defined in terms of Brownian motions. But whether there is some SPDE, I haven't really thought of it in that way. I'd say Neil is probably the person in the audience to answer your question. So let's talk about the inverse gamma polymer for the remaining amount of time. So my weights are now reciprocals of gamma variables. I fix a parameter alpha. So what happens now is that this I process becomes really wonderfully tractable. It has invariant distributions which are simply independent inverse gammas. So remember, the state of the I process was an n-tuple of bi-infinite sequences of real numbers. So what we want here then is that we want independent sequences of IID variables. So then the intertwining picture implies that if we push this forward with the D, we get a joint distribution of these Busemann functions. So let me extract some properties of what follows from all of this. So we have to map, so the Busemann process was indexed by direction vectors. So we have to map those direction vectors suitably to real parameters. So this is the mapping that does the job. So the psi1 there is the trigamma function. And what sorts of things can we get out of this? Well, we can get a few nice explicit properties. First of all, if I fix the direction parameter and I look at the Busemann functions on the entire x-axis, say, on the lattice, then what I see are independent or IID inverse gamma variables. Now the Busemann functions themselves they're real valued, so this statement is about the exponentials. So I guess one could say that the Busemann functions themselves are logarithms of inverse gamma functions. If I want to do the opposite, I want to fix a unit edge on the lattice, but let the xi parameter vary, or equivalently, let this rho parameter vary. Then I get a process that is strictly increasing and turns out to have independent increments. And the increments are logarithms of, I guess, logarithms of reciprocals of beta variables. Now, what about the path itself? What does that look like? Distributionally, we can give a complete description in terms of an inhomogeneous Poisson process. So here's how that goes. So let's take a Poisson process on the plane, inhomogeneous. So defined in this set here, the interval 0 alpha. Remember, alpha was the parameter of the inverse gamma weights, and then positive reals, and with this density here. And then I form this sort of random distribution function I take an initial value at parameter value 0, which is a log of an inverse gamma variable, and then I go along the Poisson process and I add up these vertical marks, these y coordinates. So it's kind of like a marked point process, but actually not rigorously speaking, because the ground process is dense. So it's not quite an honest marked point process in the sense that you have a locally finite point process with marks, but that's why we've formulated this in terms of this planar Poisson process. And the theorem is that this Z process gives exactly the distribution of this Busemann process across a fixed unit interval. Now, in case you wonder where is this initial value coming, why is it there, this initial value Z0, which is distributed exactly like the weight itself? Well, if you can sort of picture the situation at one limit, so you have your C direction vector. If you make it converge down to E1, then what happens is that in the limit, all your polymer paths are just straight lines. So the Busemann function there sort of trivializes into just the weight at the point there. So that's the limit that's visible there at the value 0 of that description. And let's see, how am I doing with time here? Okay, perfect. Time for one more slide. All right, so up to now I've been just describing to you features of the Busemann process. So let me give you, here's a few more features actually before I get to that. Well, I don't want to quite, okay, yeah, almost. I don't want to push, I don't want to start pushing the schedule already. So here was the process of the Busemann process, or over a fixed unit interval. Here's a picture of what it looks like. It's a pure jump process, actually, right? Because it comes from that Poisson process. But of course, you can't quite see that in a picture. The picture looks continuous, but what it actually is, it's just a dense set of jumps. So discontinuous basically everywhere. And since the jumps are the interesting thing, so let me actually talk about them a little bit. So here's a theorem about the general polymer model. Now, no assumption on the weights, just that they're just enough to make the model well-defined, IID weights. It turns out that in general, the Busemann process has this property that on every unit edge of the lattice, you see the complete set of jumps. Okay. A few relevant comments here. This is quite different from last passage percolation. So what happens in LPP is that if you follow the jumps on the lattice, they actually form a very interesting evolution along a graph, which Chris and Firas and I elucidated this in our GEMS paper that came out last year. So that's one big difference between positive and zero temperature. Now, what happens at these jumps in the polymer model? Well, what happens is that there are multiple extreme polymer Gibbs measures. So you can formulate sort of a Gibbsian theory in the polymer model in a very natural way, and then the finite point-to-point polymer distributions, they extend to these distributions on semi-infinite polymer paths. And then the question is, say, given a direction, do you have just a unique Gibbs measure or do you have multiple? And it turns out that these jumps of the Busemann process are exactly where you see multiple Gibbs measures. But here's a shortcoming, the third bullet. There's no proof presently in the general polymer model that jumps exist. So the only one where we know that jumps exist is this inverse gamma model in this particular path geometry. We know it also in some other models, but they're all of this exactly solvable type. So in other words, in the inverse gamma polymer model, we know that on each edge, we have the same dense set of jumps. And here's again a big difference with last passage percolation. If you look at an individual edge in exponential last passage percolation, the jumps are discrete in the interior of the space of direction vectors. The jumps accumulate only at the edges. But if you look globally on the lattice, you do see a dense set of jumps. All right. So finally, yeah, I want to illustrate a little bit what we can get, what sort of properties of the model we can get from knowing things about the Busemann process. So fix a direction C now. So in a fixed direction, there is no multiplicity of Gibbs measures. So almost surely there is just one unique Gibbs measure in direction C from every starting point on the lattice. So now imagine starting two polymer paths from two different lattice points, and let them run independently until they meet, and after that make them go together. They're Markov chains. That's what these semi-infinite polymer distributions are like. They're Markov chains. So it is a fact that these paths coalesce almost surely. So the question is, how fast? So there are three quantities that enter into this description of the coalescence. So there's the distance k between the starting points. There's a large parameter r for late coalescence, and then there's a small parameter delta for early coalescence. And then we have probability bounds for these events. So here are bounds for coalescence that happens abnormally late. So of course, we all know to expect that the KPZ wandering exponent 2/3 is what controls this phenomenon. So a polymer path of length n is expected to fluctuate in the transversal direction by into the 2/3. So if you start the two paired paths k apart, they should coalesce before or when they traveled on the order of distance k to the 3/2. So that's the right scaling for this problem, this k to the 3/2 here. So suppose coalescence hasn't happened by distance r k to the 3/2 for r large. So this probability goes down by like r to the negative 2/3. So it's an average probability now. So there's the quenched probability inside and then an expectation over the weights. And then here's the corresponding result for fast coalescence. The probability of coalescing before you've gone delta times k to the 3/2 goes down like an exponential of negative 1/² delta squared. So in other words, the qualitative conclusion is that we see the KPZ wandering exponent again, as we would expect. Now, these bounds here illustrate nicely the best that we can presently do without integrable probability techniques. So we're still studying the solvable models, but no integrable probability, just couplings and probabilistic arguments and reliance on these stationary distributions. So you see, so this is fairly new that we get this degree of precision just a few years. And what I mean by degree of precision is that we have actually the correct order of the probabilities, right? The upper and lower bounds coincide, except occasionally we may have a logarithmic weakening there, right? So that's sort of the current state of that subject. All right, I am at 10:06, so I guess it's a good place to stop. So next I would have talked about continuum, but I gave this KPZ talk already in October at the Simons conference, so you'll find it online if you want. So let me just finish up with this picture here. This is a simulation by Evan. It's the Busemann process of the KPZ equation. So those graphs there, they're Brownian motions with drifts. As you can see, some of them point upward, some of them point downward, and jointly they represent the Busemann process of the KPZ equation. All right, I thank you for your attention.
Any questions?
So maybe explain this, but with the inverse gamma polymers, how do you know that every edge, the Busemann process has the same jumps? So where does that come from? Does that come
Oh,
from?
that comes from like, you know, I don't know, almost 10 pages of proof.
Okay.
So at heart, it has to do with the algebraic difference between regular algebra that works in polymers versus max plus algebra that works in last passage percolation. The algebra of polymers is simply such that as the Busemann functions evolve on the lattice under these equations, you don't lose information. Whereas max plus kills information all the time, right? If I tell you that the maximum of two numbers is 3, you still don't know those numbers, right? But if I give you different algebra, you can work backwards. That's basically what it is. But then what does the proof run on? Basically ergodicity. That things are ergodic on the lattice.
In the presence of a boundary, like if you look at log gamma with a boundary, you know, there are still descriptions of the actual stationary measures. They're more complicated, but they're currently not descriptions of the sort of coupled stationary measures to different overall densities. Have you thought about how the introduction of a boundary affects your approach?
Haven't tried, no, because I've heard that your guys are on it. So, I think I'll. Yeah, but then you know that's like a signal. You know, I don't want to get burned, so I'll leave it at. Hopefully you guys will sort it out. So. Yeah, Evan.
So this last slide, you had on the coalescence estimates. So you had this kind of independent coupling where they together.
Yeah.
And so I guess it's the same, like, kind of independent of these walk from person that they intersect.
Yeah.
Potentially the other couplings of the two polymers, does it still work, or would you expect the same kind of estimates?
I don't know. How would you like to couple them?
Maybe couple them some way like where you have the same kind of like some kind of uniform variable each step on where they go up or to the right and.
But wouldn't this be the same thing? I mean, do you want them to see each other before they meet? Because yeah, that's how you might do this, right? You put some uniform variables on the lattice and the walks obey these, but once they're together, they see the same uniform and then they're together forever after. If there's an interesting coupling, yeah, one might try, but.
Principle of Busemann function should be useful in more than two dimensions. Any prospects for that?
Yeah, we certainly hope so. So Firas and his students and postdocs have done work in this direction. So you can again build parts of the general theory, but you fall a little short because you don't have the monotonicity. So the basic thing is just this silly observation, well, not silly, but the basic fact that in more than 2 dimensions, 2 curves can get past each other without touching, and that makes all the difference in the world. So one would need some kind of new monotonicity concepts, maybe but yeah, you can find some of this literature out there, and I guess Ken Alexander has done something in first passage percolation in higher dimensions for geodesics, maybe Michael also. I'm not sure, I haven't followed all of it.
Thank you, Morgan.
Okay.
Part of the couple Very much about the cameras, and it's still really nice.